Everything will begin on the surface of our star, with the formation of a colossal solar storm, and whose plumes of plasma and bursts of fury will expel gigantic jets of matter and dangerous lights that will then travel through space toward our planet. And when these intense bursts of particles and radiation finally reach Earth, they will slightly swell its atmosphere. They'll destroy our weakest satellites and bring others down. And while a geomagnetic storm in the sky gives rise to polar auroras reaching down to the equator, airplanes will be grounded. Much of the internet will go down, and the world will face widespread power outages. A disaster like this isn't just science fiction. Solar outbursts like these are actually common. On July 23, 2012, a storm strong enough to cause all I've described passed by Earth. If it had hit us head-on, it's believed it could have set modern civilization back by several months. During the Candle era, nearly 150 years ago, Earth was twice engulfed by a powerful solar storm within 3 days. And those who experienced it couldn't believe their eyes. On the night of August 28, 1859, East Coast residents saw auroras form with unprecedented intensity. You could read the newspaper at midnight using only their scarlet glow, which even reached Cuba. In the Caribbean, some residents were so stunned they mistook them for distant fires. 2 days later, the astronomer Richard Carrington noticed an unusually large group of sunspots on the surface of the Sun. Soon after, a bright white flash burst from those areas for several minutes. 17 hours later, the magnetic shield of our planet is severely disturbed and the celestial fire reignites almost everywhere around the world. In the heart of the Rocky Mountains, in the United States, gold prospectors are awakened in the middle of the night by curtains of light, and they start preparing their breakfast, thinking that the sun is rising. The arrival of this second solar storm sets both hemispheres ablaze. Auroras are seen nearly everywhere, from the poles to lower latitudes. In China, Japan, Hawaii, southern Mexico, Panama, Cuba, all over northern Europe, like Italy, Colombia, or Chile, waves of auroras turn night into day. All around the globe, instruments measuring the Earth's magnetic field go haywire, while telegraphs, suddenly overwhelmed by a massive surge of current in the power lines, are shut down, telegraph poles spark, and the most violent sparks start fires. And that's about it. Because if we set aside the minor damage caused to the few telegraph instruments of the time, the 1859 solar storm was likely a stunning visual spectacle for all who saw it, an unmatched display of beauty, which, among other things, allowed astronomers of the time to attribute the polar auroras to variations in the sun's activity. But if such an event happened today, it would probably bring part of our modern civilization to its knees. Paradoxically, we are more exposed now than ever before. Living in a connected world, a society fed on technology where electronics and satellite navigation systems are at the heart of our lives, we have become vulnerable to the whims of the sun. And since we also understand much better what inevitably awaits us, here, in broad terms, is what will happen the day a solar storm as powerful as the one in 1859 has the bad idea to strike us head-on again. By pointing their telescopes at our star, just as Richard Carrington did in his time, astronomers will observe groups of sunspots at the equator as they regularly form. The difference is that these will be abnormally large and directly above them. Within what is called the solar corona, giant magnetic loops will form, signaling a massive solar flare slowly rising into the upper atmosphere of our star. These loops, which can reach several million kilometers in length, carry with them billions of tons of material from the surface of the sun, and they are held captive by the bars. What do their intense magnetic field lines form? And when these field lines break, these kinds of plasma bubbles suddenly burst. By ejecting billions of tons of boiling matter into space, torn from the star's gravity, these massive coronal mass ejections, made of particles and ionized atoms, now blast out at hundreds or thousands of kilometers per second into the interplanetary medium. By coincidence, they went toward Earth. Roughly aligned with the plane of our planet's orbit, these streams of matter and radiation don't need to be truly precise to impact us. We just have to be in the wrong place at the wrong time. When the plasma cloud reaches Earth's orbit, it's huge, nearly 150 times the distance from 150 times the distance from Earth to the Moon. The first bad news comes when such a solar storm is directed toward Earth. that of the highly energetic light, which, emitted at the same time as the eruption, takes just 8 minutes and 20 seconds to travel the distance from the Sun to our planet. Unaffected by Earth's magnetic fields, these X-rays and ultraviolet rays will directly hit the upper atmosphere, causing it to heat up and expand, increasing its thickness by several tens to hundreds of kilometers. Satellites in low Earth orbit, like the International Space Station, can eventually fall back down because they're not truly in outer space. They are continuously slowed down by the extremely thin presence of matter, up to altitudes of about 600 kilometers. And the expansion of the atmosphere caused by a giant storm will result in increased friction, to increase the drag force they are subjected to and thus reduce their lifespan. In some cases, it can even cause them to fall prematurely to Earth just a few months later. After each minor geomagnetic storm, we had to adjust the orbits of hundreds of satellites in 2022. A relatively modest solar storm even caused the upper atmosphere to expand enough to prevent 40 Starlink constellation satellites from reaching orbit at lower altitudes, at the level of what we call the ionosphere. The energy injected by the sudden and abundant arrival of these energetic radiations will disrupt the transmission of high-frequency radio waves. And this can cause global positioning system positioning errors of several dozen meters. For an airplane, that's the difference between a runway and a few hours. After this energetic light, the first bursts of charged particles arrive, those that, being the fastest, take only a few hours to cross the distance separating us from the Sun. For astronauts aboard the International Space Station, even though they are partially protected by the magnetosphere, it's better to slip into the module equipped with shielding designed to absorb the arrival of this storm. Protons, electrons, and heavy ions, fast for many satellites in high orbit, which position more than 35,000 kilometers from the ground, benefit from only weak protection from Earth's magnetic shield. This shower of energetic particles can complicate things by straining onboard electronics. A major solar storm can shorten a satellite's lifespan by years or even destroy it within hours. In fact, even though satellite components are designed to withstand storms, the arrival of large amounts of stray currents can corrupt data and cause incorrect instructions. As they pass through, they can flip 0s to 1s and 1s to 0s. In the worst case, they might even destroy essential components. After about 20 hours to a few days, we travel the 150 million kilometers to the Sun. The vast majority of the plasma torn from the star and moving more slowly reaches our planet, and the magnetosphere, the invisible shield generated by Earth's magnetic field, is then deformed and compressed by the arrival of a shower of charged particles. It goes from being 60,000 kilometers thick in the direction of the Sun, normally, to just a few thousand at most, and after breaking through our first lines of defense, like so many invisible arrows, gigantic amounts of protons and electrons then pour into the upper atmosphere. They go on to create fantastic colored draperies almost everywhere on the planet, and maybe that's the only positive point. Because under these relentless blows, these tiny darts, auroras spread to lower latitudes, and the Sun's outbursts can even extinguish the light. Solar particles interact with Earth's magnetic field, causing strong electromagnetic fluctuations that create telluric currents, unusual electric currents in the ground with unexpected effects. During the 1859 solar storm, these telluric currents allowed some telegraph operators to keep talking, sending, and receiving messages for several hours. This still happened even with the telegraph power supplies disconnected. Nowadays, the continuous presence of these currents flowing through the ground and getting into all circuits would end up damaging a large part of electronic systems or even causing incidents, such as disabling many electrical transformers, even leading to a widespread collapse of the grid. And entire regions would be plunged into darkness, not to mention chaos. In 1989, a stream of charged particles from the Sun caused the collapse of a large part of the Quebec power grid, plunging 6 million people into darkness for 9 hours. It is now estimated that a major storm, like the one that nearly missed us in 2012, could cripple the power grids of high-latitude countries, with a global financial cost estimated to be equivalent to the material damage caused by all cyclones and earthquakes combined over the past 10 years. The big question is, when will it happen? So, the problem is that we can't predict when the next super eruption will happen, but we do know that it's more likely to happen this year than it was last year. The sun's activity follows its own rhythm, with mood swings in a strangely regular pattern. A regularity that has nothing to do with the fact that our star rises and sets in the sky with the precision of a metronome, but one that can be observed when we study the sun continuously since we began observing its surface, at least with the help of our telescopes. We have observed that our star undergoes regular and profound changes in activity, continuously alternating between relatively calm phases and others that are much more turbulent. In other words, the sun has a sense of rhythm, a rhythm whose tempo is marked by the number of sunspots that regularly appear on the surface of the star. The activity of our star increases and decreases regularly over time. Alternating every 11 years, the star shifts between turbulent and calmer phases. Since the first solar cycle was observed in the mid-18th century, solar minimums and maximums, periods of low and high activity, alternate continuously about every 11 years. At the time I'm writing these lines, we are in the 25th cycle and heading straight toward a new maximum. The solar maximum, expected in 2025, could start as early as this year. Indeed, for several months now, our star has been increasing the frequency of its eruptions as it approaches its peak activity more quickly than expected. On December 31st at 10:55 post-meridian Paris time, and while you were probably celebrating, the sun also put on a fireworks show because one of the most powerful solar eruptions in recent years broke out on its surface. The start of this intense active period shouldn't significantly affect your lives, because during solar maximums, visible light output stays about the same, unless you live at high latitudes where polar auroras become much more frequent during peak phases. Going from a few auroras per year to about 2 per month on average, you won't see the sun shining more intensely, except that gigantic solar storms seem much more likely to occur. During peak phases, we see about 50 times more flares and coronal mass ejections than usual. We also begin to see how often these terrifying events happen, because the arrival of large amounts of charged particles from the sun has a large-scale impact on the Earth's atmosphere, to the point of leaving traces that can be studied. Thus, we can detect major past solar eruptions by analyzing carbon-14 levels in tree rings, or from beryllium and chlorine in Greenland or Antarctic ice. To sum up, when energetic particles emitted by the sun strike the atmosphere, they can produce unstable radioactive elements, whose concentrations tell us a story and inform us about the frequency and strength of these eruptions. What we've found is troubling. Let's start with the good news. Solar storms as intense as the one in 1859 are relatively rare. It's believed that about 6 or 7 of them hit the Earth per millennium. On average, that's one every 150 years. Well, the bad news is that the last one to hit us did so a little over 150 years ago. And above all, we've discovered that some solar storms that hit us in the past were probably 10 to 100 times more powerful than the ones in 1859. Over the past 10,000 years, our planet has been hit by at least 3 of these supersolar eruptions. The last event was around 775, with 2 other powerful events in 5259 before Christ and 7176 before Christ. The number of past supersolar eruptions may be higher than we've found, because so far we've only studied in detail barely 20% of the last 12,000 years for traces of their occurrence. It's thought that an event 100 times stronger than the one in 1859 occurs every 800 years and one 1,000 times stronger every 5,000 years. But here's more good news. When these major eruptions happen, we don't see mass extinctions in the fossil records. Our distant ancestors surely danced around the fire at some point, illuminated by the spectacular scene, produced by the immense power of polar auroras descending to improbable latitudes. Auroras back then must have indirectly inspired new myths and gods in our minds. If one of these super eruptions were to hit Earth today, it would bring our modern civilization to its knees. Because even if the entire cloud of plasma produced by such an event passes over our planet in a few hours, even if the Earth's magnetic field returns to normal in less than 2 days, a major solar storm could take down the internet for several weeks, and its effects could be felt for months or even years. Luckily, our tech weakness is also a strength. Since today we are able to continuously observe the sun and predict the arrival of particles ejected by the bursting of huge plasma bubbles. Several days in advance, it was by trying to understand our star that we realized we have never actually experienced real solar storms. In 2012, Earth missed being exactly where the ejections passed by just 9 days on its orbit, ejected by a gigantic eruption. We won't always be this lucky. The question isn't if, but when this will happen, and what state the world will be in afterward. Nothing new? Our knowledge of the sun is full of unknowns that, like sunspots, conceal many mysteries. Who controls the seasons of the sun? What are the underlying reasons for these 11-year cycles? Why this value instead of another? Today, we still don't know exactly why, even though all the clues seem to point to the most obvious culprit, the turbulent solar magnetic field. If you're interested, I made a full video on the topic.